Hey there. In this video, we're going to practice using the table of Laplace transforms to quickly find the Laplace of a few different functions. So I've got three examples here. We'll just kind of run through some variations of what you might run into when trying to find the Laplace of a function. And you'll notice at the top right here, I have all the formulas from a table of Laplace transforms. This is not an exhaustive list, but it's the most common ones that we run into. These are the ones that you would worry about for this class. Okay, so the first one here, I have the Laplace of a polynomial. This is negative 4t squared plus 16t plus 9. And so each one of these I'm going to have to handle separately. So for part A, it's the Laplace of negative 4t squared plus 16t plus 9. If you want, you could separate those out and have a separate Laplace for each, but it's really not necessary to write that out separately. But I'm just going to take these one at a time. So I have negative 4t squared. And looking at my my list over here, here's the second one is a power of t. And so the negative 4 is really just going to kind of hang out front times. And let's see, in this case, n is 2. So I'm plugging in 2 to n factorial over s to the n plus 1. So that's going to be 2 factorial divided by s to the 2 plus 1, so cubed. Right, and so just sticking with this one, 2 factorials, 2 times 1 are 2. So I get 2 times negative 4 is going to give me a negative 8 over s cubed for the first term. And then I moved on to the second one. In this case, I'm going to use the same formula, only now n is 1. So this is going to be 16 times 1 factorial over s to the 1 plus 1, or s squared. And then the last one is a constant, so I'll use the top formula for that. The Laplace of 1 is 1 over s, so this is going to be plus 9 over s. And so finishing this off, 1 factorial is 1, so this is 16 over s squared for the second term, plus 9 over s. And this is true for when s is greater than 0. Okay, so let's look at the second one now. For part B, we're taking the Laplace of e to the t minus e to the negative t squared. Now, none of my formulas really look like this at all. I do have a Laplace of e to the at over here, so I want to be able to use that. So I'm going to deal with the square by just distributing this out. Okay, so before I actually start finding the Laplace, I'm gonna square this. So this is e to the t minus e to the negative t times e to the t minus e to the negative t. Okay, so make sure you should get at least 3 terms when distributing this out. So let's see, e to the t times e to the t is going to be e to the 2t. And then e to the t times e to the negative t is going to be minus 1. Okay, you add those exponents, you get a 0. And then I get another one, negative e to the negative t times e to the t. So actually, I'm just going to combine those to get minus 2. And then the last one is negative e to the t times negative e to the t, which is going to be positive e to the negative 2t. Okay, so these are 3 terms now that I have formulas for, so I can apply the Laplace transform to it. So e to the at, for this first one, a is going to be 2. So that's going to be 1 over s minus 2, where s has to be greater than 2. We'll see if anything else trumps that. We're going to go with the highest value of all of these and just use that for the whole expression. For the negative 2, that's the top formula, Laplace of 1. So that's going to be minus 2 over s. And then for the last one, this time the a is negative 2. So we have 1 over s minus negative 2. So that's going to be plus 2. And so the 2 is the highest value among all these. The middle one has to be greater than 0. And the last one has to be greater than negative 2. So the 2 is the greatest one, so that's going to be my restriction for all of these. Okay, one more. We got the Laplace of 10 cosine of t minus pi over 6. This was kind of tricky. Looking at our formulas, well, we have, a Laplace for a cosine function, but not one that has a sum inside of it. That's a little more complicated. So I'm actually going to use a trig identity to help me out on this one. And so the trig identity I'm going to use is cosine of alpha minus beta. I'm not going to worry about what the name of this one is, but I do want to be able to use this formula to transform that cosine of t minus pi over 6. So this identity tells me that this is equal to cosine of alpha times cosine of beta plus sine of alpha sine of beta. And this is looking pretty good to me because I can actually evaluate sines and cosines. And some of these are just going to be a number because I'm plugging in the actual pi over 6 there. Okay, so let's do that within our Laplace here. So I got the 10 hanging out front. Don't want to forget about that. It's going to be 10 cosine of t times cosine of pi over 6 plus sine of t. And don't forget about the 10. We got to have the 10 on everything. So right there. Sine of t sine of pi over 6. Okay, so either using a calculator, looking up a unit circle, however you come up with it, cosine of pi over 6 is root 3 over 2. Cosine of, or sine of pi over 6 is 1/2. So I can clean this up a little bit. So 10 times root 3 over 2, that's going to be 5 root 3 times cosine of t. And then in the second one, 10 times 1/2 will give me a 5 times sine of t. Okay, so it doesn't get much better than that. I'm ready to apply the Laplace to each of these. So the 5 root 3 is going to go into the numerator. And let's see, the Laplace of cosine of kt is s over s squared plus k squared. So that's going to be 5 root 3 times 1, since k is 1. Or sorry, times s on this one, over s squared. I'm running out of room to keep these both on the page. S squared plus 1. Okay, and the sine has a constant on it, so this is going to be 5 times 1 over sine squared plus 1. And then let's see here. So last thing I could do to simplify this, they do have a common denominator, so I can go ahead and write this as a single fraction. I'm even going to factor out the 5. So this is 5 times s root 3 plus 1 over s squared plus 1. And there's no restrictions on the s there, since we'll never have a 0 in that denominator. So those are 3 examples of how you might use a Laplace on some different functions.